Okay, this problem sort of reads like a riddle, right? So there's about three different things they're talking about, and they don't quite all, seem to relate to the same thing. So what you have to do is basically break it down into pieces, okay? And just deal with one piece at a time. So a ball is to be shot from level ground with a certain speed. This figure here shows the range it will have versus the launch angle at which can be launched. So right now, without reading any further, we know we're probably going to have to solve this problem where you launch something from level ground and find the range at least. What else do we need? We need the flight time. We need the flight time, and we got to find the maximum flight time, which is determined by picking the right theta knot. So anyway, let's just solve the problem first, or I don't mean solve the problem, but what's the phrase? Let's just do the problem that we think. Oh, that's not what I want. Let's see, what's that? That's probably okay. Sorry, still getting used to Sketchbook Express. Okay, so anyway, the problem is ball in flight over level ground. I mean, my straight lines aren't all that straight, but that first one was just horrible. So basically, something like that is what the ball does, okay? And, okay, pretend that's an explosion, not a terribly failed attempt to draw an arrow. Okay, so there's some initial speed at launch, and it says that that's certain, but anyway, you got initial speed, you've got an initial angle, which they're calling theta naught, and of course then you want to find the range, okay, and time of flight, or time o flight, if you want to be sort of Irish, will be t. And then let's go and set up our coordinates here, x, y. So the x acceleration is 0, y acceleration is then going to be negative g, standard projectile motion stuff if you go x horizontally and y vertically. Okay, so basically just looking at, on the x side of things, okay, wow, that's really bad. Let's see. The x side of things, delta x is this range here, which is unknown, okay? And then the initial velocity, so the x component of the initial velocity, and I haven't written the 0 here because, well, so what I'm going to say here is that because the x acceleration is 0, the x component of velocity is going to be constant. And this is something, this is the sort of thing you can do once you get a little practice with these and you understand that you can sort of jump ahead and say, well, find Vx is just going to be V naught cosine theta, and then I'll put a little note in here saying it's going to be constant. Okay. And what else? So the x acceleration is 0, so the time, it spends in flight, is just going to be this t. Okay. And time, remember, is going to apply on both sides. On the y side, delta y, and we're talking here about the total flight from here to here. So delta y is going to be 0, right? In the end, it ends up at the same height it started at, punk. So Vy, now there is acceleration in the y direction, so we will have to deal with a changing y velocity. So all I can say is the initial y velocity is going to be V naught times sine theta, and that's just, like with this, it's just the component breakdown of this into x and y. Okay, acceleration in y direction is negative g, and then delta t, as with over here, is t. So let's see now if I can erase. Okay, not bad. Dr. Smith. Now, which one was I on? Was I on the felt tip pen? Well, let's call it the felt tip pen. I don't think that's what I was on. Whatever. Okay, so basically now we got to solve this stuff. So it turns out if we want to use displacement and time, then really our only option is cake2. So cake2, cac2, fine, whatever. In y, I've stopped caring. Okay, we're going to say delta y is, of course, Vy naught times delta t plus 1/2 y acceleration delta t squared. And so what that gets us then is that 0 is equal to V naught sine theta times t, and then minus 1/2 g t squared. Rearrange this, basically take the 1/2 gt squared over to here, it becomes positive. You can cancel 1t, Okay, and then you can say, let's see, let me get this right. So I'm just going to go, fine, I'll do it the short way. 1/2 gt squared. In fact, I'll just show you the whole thing. Okay, v naught sine theta t, and cancel, cancel, cancel. Then the 2 over g comes over, so let's get over here and say time of flight is going to be 2g over v naught. No, wait a minute. Not quite. Actually, let me put it up here. Time is going to be 2 v naught over g times sine theta. Okay, so, oh, theta naught, sorry. So yeah, the book, or not the book, but the problem used theta naught here, so I guess I should do the same. It's the only theta I've got, so I'm not particularly worried about it, but sometimes that can trip you up, I guess. So this is one of the things the problem talks about, but let's hold off on discussing that for a moment. And the other thing would be range. So range is pretty easy now because we just take our constant x velocity equation. So this is our k2 and y, and for our constant x velocity, we're just going to say, I'll do it over here, we'll go delta x equals vx times, well, times delta t, right? And vx we know, delta t we know, and this is going to be range, right? This is going to be r. So I'm just going to substitute in right up here because it's going to come out to be exactly what we want. V naught cosine theta. Oh, you know what? Actually, let me do one substitution. Yeah, I shouldn't have. Oh. So I hope I'm at least teaching you that it's okay to not quite have a clear idea of what you're doing and to make mistakes occasionally, and you don't have to be neat, okay? Don't be afraid to just dive into a problem and start doing stuff, okay? V naught cos theta naught. And then t here, we're going to plug in 2 v naught over g times sine theta, okay? And then finally what we're going to get is r equals, and I'm going to go 2 v naught squared over g, and then this is going to be cosine theta naught sine theta naught. And what you may remember from trig is 2 cosine theta naught sine theta naught is equal to sine of 2 theta naught, okay? So the 2 and the cosine and the sine turn into sine of 2 theta, or 2 theta naught. And that's useful here because what we're going to do is look at r equals, I'm going to write it this way, okay, v naught squared over g times sine of 2 theta naught, okay? So now, this gives t and r symbolically. We have a fixed speed, a fixed launch speed v naught. It says a certain launch speed, right? We have a fixed g because we're always on the same planet. So it's theta naught that varies. So one thing they talk about is t max, which is the maximum time of flight. Let me just get back to QuickTime and make sure. I don't know. Okay, I'm just guessing I have enough time. All right. So, okay. So what's the maximum value for time of flight? Because they talk about the maximum time of flight. This is the time of flight here. It varies with theta naught. So what's the maximum value? Now, if you're in calculus, you can just go, oh, dt d theta, set it equal to 0, la 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 la, solve for the maximum. And that's great. If you want to do that, go ahead. If you don't, or if you're not in calculus and you don't know what that mumbo jumbo I just said was, that's fine. What we can do is we can look and say, okay, v naught and g are fixed. What's the maximum value we could get out of sine? The maximum sine for any angle is 1, right? Can't have a higher sine than that. What angle has a sine of 1? 90 degrees, okay? So what that means is that at 90 degrees, when sine theta equals 1, that's when you have maximum time, right? Because that's going to give you the maximum value for this. So t max then equals 2 v naught over g. And in fact, now you can use this to solve for v naught. Remember, it's fixed, but not given, okay? G is given. Well, I mean, g is obviously given. T max, they don't. So what do they do? Actually, you can't quite find out T max. Wait, can you? No, you can't. Actually, you don't know T max yet. Okay, but this gives you something at least. Okay, so we don't know. We actually can't do anything with that yet. My bad. All right, let's look at this now. Range. We have this plot for range, and that was, I'm afraid to go back to my browser because I'm afraid of what window it'll take. I mean, not that I'm in any bad windows, but I don't want it sweeping across and showing your grades or something. So, you know, or showing my game of Candy Crush or whatever. So we had a plot of r versus theta naught, okay? And what you could do here now, for one thing, you could, what's important to get off of here is the maximum range, right? So where's this maximum range going to go? If you think about it a little, it's pretty obvious. This is going to be theta naught equals 0. This is going to be 90 degrees, because in both cases, you get no range on the projectile. If your elevation angle is 0, it just plops into the ground right after you throw it. If your elevation angle is 90 degrees, you throw it straight up and it comes back down in the same spot. So think about it a little, and then by the fact that this is symmetric, you can guess this is going to be 45 degrees. And if you look here, you say, well, theta naught 45 degrees means you're taking sine of 90 degrees, and that's 1, right? So that would give you your max range. So you can pull R max off the plot. And then you can say, so this is going to be 1 when you're at maximum range, right? So R max is equal to V naught squared over G. Now you actually can pull R max off that plot, okay? Whatever it was, the very top, they tell you how many spacings. It's WebAssign's silly way of, randomizing these plot questions is just changing the scale of one axis, whatever. So you can find V naught through this is the point. So you can go V naught equals square root, and then this is going to be G times R max. Okay, that gives you V naught, and then you can now plug that in for T max. Sorry about the ding. That's Mr. Hannum sending me email, and it's 6:50 in the morning on Wednesday. I would give him grief about sending an email at 6:50 in the morning, except that I'm here doing a video, so I kind of can't really. Okay, so anyway, T max then is, you can plug this in if you want, I guess, but you could just find V naught, numerically. So fine, I'll do it symbolically. T2, what's it going to be? 2, and then you have the V naught, so it's going to be 2 root, and then you're going to go, the V naught is on the top, R max, and you have a square root of G, but then if you want to bring the G inside, that becomes G squared. So like this, where G is definitely inside the square root. And just when you do something like this and you get something like that, and you're like, is this right? One thing to check is always units, okay? So R max would be in meters, say, and G was in meters per second squared. So you take meters, divide by meters per second squared, you get like 1 over second squared. So you get 1 over second squared, which then is equal to second squared. Remember, the denominator of a denominator becomes the numerator. And then, of course, that's all in the square root. So that's going to give you seconds, which checks out with your Tmax. Okay. So great. This now gets you V naught. And finally, the question was, what's the minimum horizontal velocity? Or what's the minimum speed it gets? So I'm not sure how long this video has gone, so I'm going to stop this video and probably start a part 2 before I go over YouTube's time limit. Okay, so we'll see if I can get to part 2.